proposition is undecidable. So what do I mean by non-trivial proposition is that if you want to say something on every program, for instance, something which is independent of the number of a program. Okay, you want to ask a property of a program. For instance, whether it will stop, whether at some point the pixel will be red or whatever. Okay, but something which has to be related to the behavior of the program. Every time you ask a question on the behavior of a program, the only question you can answer are the ones for which this is true for every program. Okay, so just forget about what I said. But basically, the problem is quite hard. Okay, so now we are in a much more problematic setting. Is that as soon as our model is powerful enough, then we are doomed. There are a lot of properties that we won't be able to prove on it. Okay, and there is nothing we can do. Bon. Okay, but some properties are decidable. For instance, I want to know what the weather will be like tomorrow. Okay, I just have to wait until tomorrow. Okay, that's decidable. Okay, there are other questions which are decidable. For instance, whether this specific pixel in life will turn black at before time 10,000, for instance. Okay, this is a decidable question. I just have to run life for 10,000 steps, and I will know. Okay. But this is not exactly what we want to do. We want to predict. We want to be able to tell in advance without simulating it. Okay? We don't want to spend a lot of time simulating life. We want to know whether this pixel will be black or not at 10,000 now. I don't want to wait for 10,000 steps. Okay? Turns out it's not possible. Okay? So this is a very nice situation. We have the complete knowledge on the initial configuration. We have the complete knowledge of everything. We have plenty of time. The only thing we want to do is just to have the answer a little bit sooner. Okay? And the answer is no, it's not possible. And why is it not possible? It's because basically, as soon as you're able to emulate Boolean circuits, which is the case of life because it's Turing complete, you can simulate any computation. Okay? Then you're P-complete. So what does this mean? So basically in computer science, we have a big problem. It's that we are not really able to prove that things are hard. That's another question, to prove that things are hard. So the only thing that we are able to do is, and it was quite successful until now, is to prove that some problems are harder than others. So how do we do that? Is, for instance, we do reductions. So imagine that you have a problem A, okay, and you want to show that the problem B is harder than A. So how do you do that? You just show that you can reduce the resolution of A to the resolution of B. That means that you can convert some instances of A into an instances of a problem of B. So how do I do that? For instance, a simple reduction is exiting a room is harder than finding the door. Okay, because once you found the door, you just exit. Okay, so that's basically this idea that you use. Okay, you find a way to convert your problem into another one. So, can I give you some concrete example of that? So imagine that a very trivial one. Okay, you want to compute. You have a graph here. So everybody is familiar with graphs. Okay. So you have a graph. It's a bunch of nodes with a bunch of edges between them. Okay. And you ask the question: what's the biggest number of unconnected nodes? So here, for instance, I can find 2 nodes which are not connected. But okay, let's say that, and I have 3 now. I have 3 nodes which are not connected with each other. Okay. All of them, there is no edge in this set of nodes. And I want to find the biggest set of nodes for which there is no connection between them. Okay? And you can imagine that there is another problem where you want to find the biggest set of nodes where everybody is connected. So for instance here, we have 4 nodes where everybody is connected with each other. Okay? So it's really easy to reduce, to show that these 2 problems are equivalent, because what you do is just you start from your input, original input, okay, and when there is an edge, you remove it, and when there is no edge, you add one. Okay? And what you discover here is that when you're done with that, basically a set which wasn't connected before is a set which is fully connected afterwards. Okay, because you flip the state of the edge. Okay? So we've done a very basic prediction. So most of them are much more sophisticated. Okay? But basically what computer science have shown is that you don't want to wait forever in front of your computer of the answer. Okay? So what forever means? What forever means? And there was quite a debate, but there is something like, for instance, when you have to decide when you stop recruiting students, okay, you look for a gap between the grades. Okay, at some point, you have to decide that you will recruit students up to the rank 100, 110, 109. How do you do that? You just choose the place where the gap is the biggest between the one and the next. Okay, that's a reasonable way to do it. Okay, so that's basically how computer science decided what forever means. And basically, what turns out is that you have a pretty continuous range of algorithms that are acceptable, and these are the ones that takes polynomial time. So what do I mean by that? Is that if you have an input of size n, for instance n file to sort, okay, your algorithm will give you the answer in a time no larger than n to the c, for some c. Okay, small c, if possible. Okay. And that's usually you wait for before your computer for a few moments, and you will end up getting the answer. So why is it nice, this polynomial thing? Is that, for instance, if you double the size of the problem, okay, the time, if you double the size of the problem, the time will be multiplied by 2 to the c, okay, which is a constant. Okay, so doubling the size of the problem will multiply the time by a constant, which is reasonable. Okay, this is something which is acceptable. Okay, and on the other end, there are exponential time algorithms. Exponential time algorithms are, for instance, where you do an exhaustive search. Okay, for instance, you want to sort files, and you try all the permutation until you find one in which the files are in order. Okay, so this is a very stupid algorithm. Okay, but it works. Okay, so you can patent it. And anyway, and sue everybody who would give you a better algorithm later on. Anyway, so what's going on here is that if you have a time which is 2 to the n, okay, your time to solve an issue, to solve a problem, doubles as soon as you increase by 1 the size of the problem. And this is a huge problem. There is a huge gap between these two situations. Here, you just double the time. You just double the time when you just multiply the time by some constant when you double the size of the problem. Here, in that case, you double the time as soon as you increase by 1. Okay, so there is a huge gap here. So here, it's really waiting forever. I mean, as soon as you have more than 20 files to sort, or even 5 files to solve, this algorithm that just try every permutation will just take forever. Okay, while a polynomial one will give you the answer almost immediately. Okay, so there is a huge difference here between what can be done in polynomial time and what can be done in exponential time, and that's basically where here it's acceptable, and here what takes forever. Okay, that's basically where we put the frontier in computer science. Okay, so it turns out that for the same way there exists some universal Turing machine, there exists some kind of universally hard problems among the polynomial ones. What do I mean by that? Is that you can show that here, if you name P the set of problems that can be solved in polynomial time, you have a bunch of problems that are called NP-complete,